mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Hi, welcome back to Grade 11 Physics, Day 2 of online learning. Yesterday you were reading some information on how particles are charged and what charge is on particles. Today we want to look at once a particle is charged, it has an electric field around it, and that electric field creates forces of either attraction or repulsion, and we want to look at what that means. So, a scientist by the name of Coulomb was experimenting with this and came up with some information that will be important for us as we develop what is called Coulomb's law. And so as he did experiments with charged particles, he realized a few things. He realized that, first of all, there was a force that was present when the charged particles were brought near together. And the first thing he noticed was that the force was inversely proportional to the distance between the objects squared. So if we had two objects that were this far apart, then there was a force. If we moved them further apart, that force got less. Makes sense. And it was what's called the inverse square relationship. So it was 1 over r squared, r being the distance between the two particles. So again, that makes perfect sense that if we have two charged particles, the further apart we move them, the less the force will be. And again, if we relate that to magnetism, and you've all played with magnets, further apart the magnets are, the less the force of attraction or repulsion is. So the second thing that he realized was that that same force was directly proportional to the charge on the two particles. Now you'll notice I wrote Q1 and Q2. So Q is the symbol for charge. And so when we're talking about charge, just like V is the symbol for velocity, T is the symbol for time, D for displacement, Q is the symbol for charge. And what he realized is that when we had two charges, the greater the charges, the greater the force. And again, that makes perfect sense. If we had magnets again, if we had stronger magnets, there would be a greater force, weaker magnets, a smaller force. And so charged particles the same way. So when he put these together, he came up with the proportionality statement that force is proportional to the charge on particle 1 times the charge on particle 2 divided by the distance squared between the two particles. Let's talk a little bit about charge itself. What is charge? Well, charge is extremely hard to measure and it's related to force. And Coulomb didn't really explain what charge was, other than that he measured it in a unit called a Coulomb. So charge is measured in coulombs. And what Coulomb defined it as, he said, well, one electron, so we'll go 1e, has a charge of 1.6. Now we're going to round it to 1.6. There's a few more decimal places after the 1.6, but we'll leave it at 1.6 times 10 to the negative 19 coulombs. So it's a very small number. One electron has a very small amount of charge. And so when we're talking about things that have charge, something like a coin. If you had a coin here and it was negatively charged, it might have like times 10 to the power of 6 coulombs of charge in a simple coin. And you would never even feel that, right? Small amounts of charge in these things. And as Coulomb continued to do experiments, he took his force proportionality statement, which again if you look at proportionality statements, and you'll get some questions that will deal with proportions. If we had two charged particles that were a certain distance apart, if we doubled that distance apart, then the force would become 1/4 of what it was. Because if we put a double in the denominator here and we square it, that's going to become 1/4 of what it was. If we were to double the charges, then if we double both charges, then again we're going to be 4 times greater. If we double just one charge, then we're going to be 2 times greater. If we double a charge and triple a charge, well then our force is going to be 6 times greater, right? So we can use these proportionality statements to come up with that. But he also came up with a formula. So again, when we graph things and we find lines that model this situation on a graph, we can of course find a constant that will allow us to change a proportionality statement into an equation. And so Coulomb did that, and he found that the equation was and that equation became F equals K for constant, and I'll define what K is momentarily. Q1, the charge on object 1, Q2, the charge on object 2, and over the distance between them squared. I will tell you at this point that sometimes this R is written as a D squared. Depends on which resource you're looking at it. They mean the same thing. R would be if they were circling one another, it's a radius between the two. D would simply be distance between the two, but it doesn't matter whether it's an R or a D. I'll be giving you questions that have multiple resources, and you will see both R and D squared. So K is the constant. It's Coulomb's constant. And Coulomb's constant, K, is equal to 9.0 times 10 to the 9 newtons meters squared per Coulomb squared. And that is a number that you will get to know quite well, and you will want to, well, you will just memorize it. It's an easy one to memorize, 9 times 10 to the 9. And the units will all cancel out. We've got meters squared in the denominator. We've got Coulomb squared in the numerator. When we put our numbers in, they'll cancel out, giving us a force in newtons. All right, so that's where I want to leave it today with this formula. F equals K, Q1, Q2 over R squared. And you are now going to turn in your textbook and you're going to do the assignment. I'm not going to give you an example on this because the questions you're going to get are going to give you all the information except for one piece, which you will then solve for. And I think you can do that without an example. But in your textbook, you can flip to page 552, and you can do questions 9, 10, and 11 there. And then on Connect, I'm also going to post a PDF of another page from a different textbook that will have 3 more questions for you to do on there. So in all, you'll have 6 questions to do dealing with this formula. There is a vector component to this as well. On the assignment that you're going to be doing today, everything's going to be in a nice straight line. Tomorrow as we come back, we're going to look at what happens if there's more than 2 charges and those are in various angles to one another. And we'll look at the vector nature of some of this. And we'll just do some examples that will deal with this formula, dealing with it in a vector nature. So all the best. We'll see you tomorrow. Your verse of the day today comes from Zechariah chapter 14, verse 9, where it simply says, "The Lord will be king over the whole earth, and on that day there will be one Lord, and his name the only name." Have a great day. See you tomorrow.